Hi, welcome to Modern Optimization Methods. Today we will introduce the fifth part of Chapter 9, the hypergraph matching problem, and how we apply quadratic penalty method to solve it. Recall that in the previous part, we have introduced the hypergraph matching problem as well as its mathematical formulation. Now recall that the mathematical formulation for hypergraph matching takes the following form. We minimize a multilinear function f subject to some equality constraints as well as a 0, 1 constraints. Notice that the 0, 1 constraints actually means that this problem is a discrete optimization problem, or more specifically, it is a 0, 1 integer programming problem, which is in general NP hard to solve. Therefore, in this part, we will mainly discuss how we can design some algorithms to solve this problem. Okay? Now, recall that in these equality constraints, it actually means that for each block of this vector x, the sum of these components to be 1, okay? And then we have a constraint x is either 0 or 1. In other words, in each block, there can only be one component, which is 1. The other component should be 0, okay? So from this point of view, we can reformulate this problem as a sparse constraint optimization problem. We write it in the following part, okay? So the objective function is the same as before. Equality constraints are the same as before. However, for the 0, 1 constraints, we rewrite it as a lower bound constraints as well as a sparse constraints. The 0 norm here actually means the number of the non-zero elements in X. In other words, this constraint basically says the non-zero elements in vector x should not be greater than n1. Okay? So recall that we also have a constraint, the sum of each block to be 1. Therefore, combining the two conditions here, we can actually have that for each block, there could only be one non-zero element, which is 1. And for the rest of these components in this block, it will always be 0. So this is a sparse constraint formulation. And from this point of view, we can have different ways to solve these sparse constraint optimization problems. For example, the hard thresholding type-based algorithms as well as the L0 penalty-based algorithm. Also, we can use the LP regularization algorithms to solve it approximately. So these are different ways or different algorithms based on the 0 norm constraint. Okay? Now, what we are going to do is that we relax this problem based on the 0 constraints. Okay, so we just drop the 0 norm constraint. So we get the following relaxation problem. Okay, this is the equality constraints and the lower bound constraints. And this relaxation problem is actually the same as the following one, where we got extra upper bound constraints. X is greater than or equal to 1. The reason is that by these equality constraints and non-negative constraints, we can see that for all the components in X, it cannot be greater than 1. Okay, so the two relaxations, they are the same. So as we mentioned in the previous part, the traditional relaxation is this one. Okay. However, there is no theoretical research or theoretical investigation on what is the relationship between the relaxation problem with the original problem. Therefore, the motivation of our method is that we first study the relationship between the relaxation problem with the original problem. Okay? So, surprisingly, we can prove the following results. The relaxation problem actually admits at least one global minimization of the original problem. Okay? So the mathematical statement is like this. There exists a global minimizer x star of the relaxation problem such that the zero norm is exactly n1. Furthermore, in this case, x star is a global minimizer of the original problem. In other words, the optimal solution of the original problem is actually a subset of the optimal solution of the relaxation problem. Okay? So which is very nice. In other words, the original problem and the relaxation problem, they share part of global minimizers, and of course the optimal function value is the same. Now we also give an example how we can achieve a global minimizer of the original problem by doing some modification to the global minimizer of the relaxation problem. Okay? So here is an example that if we have a block Y, which is a global minimizer of the relaxation problem, then how we can get a global minimizer X of the original problem? Then we just pick up one of the non-zero elements and set them as 1. The rest elements we set as 0. For example, for this Y1 block, we can have 3 different cases of X star, okay? Then X star is one of the global optimal solution of the original problem. So the result is actually very nice. So the remaining problem is that how we can solve the relaxation problem. Now, to solve the relaxation problem, the idea of our algorithm is different from other existing methods. So the idea here is that we try to identify the non-zero elements of the global minimizer of the relaxation problem. Why? Because as we demonstrate in the theorem, if we can successfully identify the non-zero elements of the global minimizer of relaxation problem, then we can use the algorithm we just demonstrate to get a global minimizer of the original problem. Therefore, the non-zero elements, which we call the support set, is very important. So we try to identify the support set of global minimizers in the relaxation problem. So the scale of the global minimizer is not that important. We try to identify the support set, okay? So based on such analysis, the equality constraint is not that important. So it may not be necessary to restrict these elements X to 0 and 1. We may give them more freedom to change in order to identify the support set. Therefore, we penalize the equality constraints into the objective part by quadratic penalty method, and we solve the remaining sub-problem here, okay? So the non-zero part, we also keep it as constraints. However, if we just solve this subproblem, it is not well defined because, as we may remember that this fx is a x power 3 objective function. It will go to minus infinity as x tends to infinity. Therefore, we need to add some bounds to this feasible part in order to keep this problem well defined. That's why we add an upper bound here to solve the subproblem, this one, okay? Actually, this quadratic penalty term or this quadratic penalty function is actually the quadratic penalty function to the original problem, okay? We can just rearrange our original problem by putting it a upper bound here. This m is greater than or equal to 1. Therefore, this constraint is equivalent to x between 0 and 1, okay? Therefore, the quadratic penalty method to this problem is exactly this one, okay? In other words, when we solve the subproblem, we solve this subproblem instead, all right? This is well defined. Now, we give the quadratic penalty method. So in the first step, we give initial point and give a quadratic penalty parameter sigma 0. Then we solve the subproblem to get a global minimizer xk. Notice here that we assume we can get a global minimizer xk. Then we check the termination rule, and if it does not satisfy, then we increase the penalty parameter and the iteration goes on. Otherwise, we will stop and project this xk to the assignment matrix, okay? Now, you may wonder, what is the convergence result? So, for this quadratic penalty method, we have the traditional result as we introduced before. So, for each xk, we assume that this xk is the global minimizer of subproblem. And then by driving the penalty parameter sigma k to positive infinity, we can prove that for any accumulation point of xk, it is a global minimizer of the relaxation problem. In other words, the quadratic penalty method can return us a global minimizer of the relaxation problem. However, a question is, can we return a global minimizer of the original problem? Because we are trying to recover the original problem. Okay, so as we discussed before, the quadratic penalty method have the property that we have to drive sigma k to infinity in order to make the limit point to be a global minimizer. However, notice here that we try to identify the support set, okay, of the global minimizer of the relaxation problem. Therefore, can we get more interesting results in terms of support set? Okay, the answer is yes. We can actually prove that under reasonable assumptions, when the iteration quadratic penalty parameter sigma k is large enough, then we can successfully identify the support set of the original global minimization problem. Okay, so this is what this theorem 3 and theorem 4 talks about. Okay, so basically the two theorem tells us that the quadratic penalty method enjoys the exact recovery result in terms of identifying the support set of the global minimizer of the original problem. Okay, so this is a very interesting result. Right, let's take a look at how we solve the subproblem. Okay, so the subproblem is like this. We try to solve a nonlinear program with box constraints here, right? X is greater than 0 and smaller than m. So what do we solve? We use the method called active set-based method. And the algorithm was originally proposed by Basegas in 1982, which is an old method, and we modify it into the projected gradient method. Okay, so this method is actually specified to identify the support set as well. So that's why we choose this method to solve the subproblem. Now, finally, let's present some numerical results. So here we compare our method QPPG and QPPG2 with the four existing methods. And we use the three measurements. The first one is accuracy, which means that how many correct graph matching we can get over all the matching pairs. The matching score actually means that the largest matching objective function we achieved, okay? And the third one is running time. Of course, the shorter the run time is, the faster the algorithm is. And for the first two, accuracy and matching score, the larger they are, the better the algorithm is, okay? Now, let's first take a look at the first test. We demonstrate whether we can successfully identify the support set of the original problem, okay? So this is for one specific example where N1 and N2 are all 30, and at the first iteration, we cannot identify the non-zero elements because all of them, they are non-zero. And after 21 iterations, we can see that there are some elements which are significant larger than 0, okay? Finally, when the algorithm terminates, we can see that we can successfully identify the correct support set of the original problem. So this circle here are the non-zero elements, the true non-zero elements, okay? Now, the second example basically demonstrates that the comparison of our method with the rest four methods. So the red line is our method. As you can see that we can get comparable accuracy with RRWHM method, and we are better than the other three methods. For the matching score, our method is also performs very good. And also for the CPU time, it is just the medium performance, okay? And this figure basically shows that how we match the two houses. Now, the third problem is that for some larger size of problems, we also do similar tests and the conclusions are basically the same. And this figure demonstrates that how we match a fish data set, okay? So we can successfully get the matching score to be 1, okay? Now, let's make a brief summary about this part. So in this part, we actually discuss how we apply quadratic Penty method to solve the hypergraph matching problem. And we also demonstrate interesting results to show the efficiency of the method. If you are interested in this talk, then you can check the reference here to get more details. Okay, we stop here and see you next time.